You are about to take a journey from which there is no coming back. This is the promise of the Krasnikov Tube, a one-way ticket through time and space grounded in the real mathematics of Einstein's general relativity. By the end of this, you will grasp how a theoretical tunnel in the fabric of reality could function and what its staggering consequences would be for humanity. We will uncover how such a tube might be built and confront the terrifying paradoxes that come with a door that only swings one way. If you could step into a future you can never leave, what would you hope to find there at its heart? A Krasnikov tube is a one-way street carved through the cosmos itself. It is not science fiction, but a serious, albeit hypothetical, solution to the equations of Einstein's general theory of relativity, first proposed by the Russian physicist Sergei Krasnikov. Think of it not as a tunnel with walls you can touch, but as a reshaping of the very fabric of space and time. This reshaping creates a shortcut, a cosmic subway line where the normal rules of distance are bent. But there is a profound and absolute catch. This subway line has no return ticket. Once you enter and travel in its designated direction, you are committed. The tube's geometry permits a journey that, to an outside observer, would appear faster than light, but only for one-way travel. You could use it to go to a distant star, but you could not use the same tube to come back home. This creates a permanent link, a pipeline to another point in the universe, yet it forever severs the possibility of a simple round trip. The universe, it seems, allows for these shortcuts, but only if we are willing to leave the past definitively behind. Building such a one-way street requires a cosmic architect who can redraw the map of reality. The secret lies not in building walls, but in warping the stage upon which the universe performs. This stage is space-time, a single flexible fabric that intertwines the three dimensions of space with the relentless forward march of time. Under normal circumstances, this fabric is flat and rigid, dictating that the shortest path between 2 points is a straight line. But Einstein's equations reveal that this fabric can be bent, folded, and twisted. A Krasnikov tube is a deliberate, permanent crease in that fabric. It creates a region where the very rules of geometry, what physicists call the metric, are rewritten. Inside the tube, space is compressed ahead of a traveler and expanded behind them, effectively creating a sliding sidewalk through the cosmos. You are not moving faster than light through normal space. You are taking a drastically shorter path because the space within the tube has been fundamentally altered. This concept shares a family resemblance with another theoretical engine, the Alcubierre warp drive. Both ideas manipulate spacetime to achieve apparent faster-than-light travel by contracting and expanding the fabric of the universe. But here is the critical divergence that makes the Krasnikov tube so unique and so final. An Alcubierre drive is often imagined as a bubble that a ship carries with it, a distortion that can theoretically be turned on and off. The Krasnikov tube is different. It is a fixed piece of cosmic infrastructure, a permanent tunnel that is laid down during an initial one-time passage. Think of it like paving a road. The first journey does the hard work of warping spacetime into this new, stable configuration. Once that path is set, it becomes a one-way street for all who follow. The geometry is locked in, permitting travel only in that single, predetermined direction. This is not a vehicle you steer, it is a road you enter, a road with no off-ramp back to the past you left behind. The man who mapped this one-way street is Sergei Krasnikov, a Russian theoretical physicist dedicated to exploring the furthest edges of what Einstein's equations allow. While his name is now tied to a thought experiment of cosmic finality, his work is rooted in the rigorous and often playful world of theoretical physics, where mathematicians ask what if and then follow the numbers wherever they may lead, no matter how strange the destination. The 1990s provided the perfect backdrop for such a radical idea. This was a golden age for exploring the wild implications of general relativity, a time when physicists like Miguel Alcubierre were publishing their own blueprints for warp drives and wormholes. The scientific community was actively dissecting the real physics behind what was once pure science fiction. Krasnikov was not simply dreaming of starships, he was tackling a specific problem within these models, particularly the challenge of causality and the universe's staunch prohibition on time travel paradoxes. His one-way tube emerged as a potential solution, a cosmic loophole that seemed to permit incredible journeys while carefully and deliberately slamming the door shut on any return trip to the past. It was the product of a mind willing to let the mathematics dictate the rules of the game, even when those rules painted a picture of a universe with permanent exits and no way back. This one-way nature is not a design flaw but the very foundation of the tube's existence. It is a feature forced upon it by the unforgiving laws of physics, specifically by the brutal geometry of spacetime itself. To understand why you can never go back, you must think of the tube not as a static tunnel, but as a cosmic river flowing with immense power. Once you step into this river, you are carried along by the current. Going with the flow is effortless, a swift journey downstream, but turning around to swim back upstream is not just difficult, it is fundamentally impossible. The current is simply too strong. Inside the Krasnikov tube, this current is created by the warping of spacetime. The fabric of the universe is contorted in such a specific, permanent way that it creates a preferred direction, a downhill slope through reality. The geometry of the tube is engineered to push everything in one direction from the entry point toward the exit. This is not a gentle push either. The forces at play are monumental. Think of the tidal forces near a black hole, where gravity pulls so much more strongly on your feet than on your head that it would stretch you into a strand of atoms. The Krasnikov tube generates similar, though differently oriented, extreme tidal forces. These forces would not just prevent your ship from turning around, they would tear it and you apart if you tried to fight the current. The tube's architecture makes the return journey through the same passage a physical impossibility. It is a door that swings only inward, and the moment you cross the threshold, it locks behind you forever. So what would compel anyone to take such an irreversible journey? The sheer scale of this undertaking defies human comprehension. To construct a Krasnikov tube, you would not be assembling steel and concrete, but manipulating the fundamental geometry of the universe. The first and most impossible hurdle is the energy requirement. You would need to gather an amount of energy that rivals the total output of entire stars, and you would need to focus it with a precision we cannot even dream of. This energy is not for powering engines, but for prying open the fabric of spacetime itself, creating the permanent warp that defines the tube. The mathematics suggest you would need something even more bizarre than vast energy, something called exotic matter. This is not normal atoms, but a theoretical substance that possesses negative energy density. Think of it as a kind of anti-gravity glue. Normal matter gravitates, it pulls things together. Exotic matter would do the opposite. It would push spacetime apart, providing the outward pressure necessary to keep your cosmic tunnel from immediately collapsing into a black hole. We have no idea if such matter can even exist in stable, macroscopic quantities, let alone how to produce or contain it. Then there is the question of scale. Would this tunnel be a subatomic filament, a thread finer than a human hair, or a vast passageway large enough for a generation ship to sail through? The energy and exotic matter requirements scale with the size, making a human-sized passage a project of literally astronomical proportions. It is a construction project that would require harnessing the power of suns and manipulating materials that defy our current understanding of physics. For now, and for the foreseeable future, the Krasnikov tube remains a ghost in the equations, a powerful idea that shows us the limits of what might be possible, while reminding us why it remains utterly beyond our grasp. This distinction between a one-way street and a potential round trip is the very thing that separates a Krasnikov tube from its more famous cosmic cousin, the wormhole. It is easy to lump them together as shortcuts through space, but their fundamental natures could not be more different. Think of a classic, traversable wormhole as a cosmic subway system with a station near Earth and a station near a distant star. You could, in theory, buy a ticket and take the train to that star, and then you could just as easily board a return train and come back home. The tunnel, if it remains stable, allows for two-way traffic. It is a bridge connecting 2 points. The Krasnikov tube is not a bridge, it is a chute. You slide down it, and there is no ladder to climb back up. Both structures are valid solutions to the complex equations of general relativity, meaning the math says they are possible. But the math also imposes its own strict rules. A standard wormhole's two-way nature is what makes it so vulnerable to paradoxes, to the possibility of going back in time and creating universe-breaking contradictions. The Krasnikov tube sidesteps this entire problem by its very design. Its permanent, one-way geometry erects a firewall against paradox. It allows you to move forward through space in an incredible way, but it absolutely forbids any movement backward in time. You can journey to the future of a distant world, but you can never return to the past you left behind. So while both ideas involve bending space, one offers a potential commute and the other demands a permanent relocation. So why does the universe seem to hate the idea of a round trip so much? The answer lies in the delicate fabric of causality, the simple and intuitive rule that cause must always come before effect. You cannot have an echo before the sound that created it. This principle is the bedrock of reality, and faster-than-light travel in almost any form threatens to shatter it. The moment you can outtrace a beam of light, you are effectively racing the flow of time itself. This opens the door to the most famous of all time travel nightmares, the grandfather paradox. Imagine you use a magical two-way tunnel to travel back in time and prevent your own grandfather from meeting your grandmother. If you succeed, you would never be born. But if you were never born, you could never have gone back in time to stop the meeting. The event becomes a logical loop with no beginning and no end, a contradiction that reality simply cannot accommodate. The Krasnikov tube, as a form of effective faster-than-light travel, initially seems to invite this exact problem. If you could instantly send a message to a distant star, and that star is 10 light-years away, an observer moving at a different speed might see that message arrive before it was even sent. This is the causality violation in its simplest form, and it is why physicists often say that faster-than-light travel is synonymous with time travel, and time travel breaks causality. But the Krasnikov tube has a built-in safety feature, its absolute one-way nature. By making the return journey through the same tunnel a physical impossibility, it slams the door shut on the most straightforward path to a paradox. You can go forward to the future of another world, but you can never loop back to the past you left. The tube acts as a cosmic valve, permitting a flow of travel and information in one direction only. This does not entirely eliminate the potential for causality headaches, as the complex interplay of different reference frames in relativity can still create tricky situations. Yet, by forbidding the simple round trip, the Krasnikov tube transforms from a universe-breaking time machine into a permanent, one-way relocator. It trades the possibility of paradox for the finality of a farewell, a price the universe might just be willing to accept. Stepping into the Krasnikov tube would be nothing like the smooth glide of a science fiction starship. You would not hear the hum of engines or feel a gentle acceleration push you back into your seat. The first sensation might be a profound and unsettling silence, a complete absence of the familiar vibrations of travel. You are not moving through space in the conventional sense. Instead, the space around you is moving, carrying you along like a leaf on a cosmic river. The view from your window would be a breathtaking and terrifying distortion. The stars ahead would not simply grow brighter, They would blue shift into a single, searing point of ultraviolet radiance, while the stars behind you would redshift into a deep, empty crimson and then vanish into imperceptible darkness. There would be no tunnel of light, only a violent warping of the celestial map, as if the universe itself is being crumpled and stretched around your vessel. Time itself would become a fluid and personal experience. For you, inside the tube, the journey to a star 10,000 light-years away might feel like only a few hours. Your watch would tick normally, your heart would beat at its usual pace, but back on Earth, millennia would be passing. This is the brutal reality of time dilation, magnified to an extreme degree by the tube's warped geometry. You'll be cutting a deep, narrow path through time, arriving at your destination in what feels like an afternoon, only to find that everyone you ever knew has been dust for centuries. The physical strain would be immense. The tidal forces within the tube, the differential pull of gravity across your ship and your body, would create a constant groaning pressure. Every molecule of your being would feel a subtle, relentless pull, as if an invisible hand is trying to gently stretch you into a new shape. It would be a journey of profound isolation, a one-way trip through a distorted reality that challenges every human sense of place, time, and self. You would be a passenger on a current that flows only forward, watching the past vanish into an unreachable darkness. That final, irreversible step into the tube is a leap of faith into a future you can never leave. You are not a tourist on this journey, you are an immigrant to a new era. The first and most terrifying question is not how you will get there, but what you will find when you arrive. Would you aim for a specific year, a particular century marked in a history book you brought with you? The target is not a date, but a destination for the rest of your existence. Imagine targeting a star 1,000 light-years away. Your journey through the tube might feel brief, but on Earth, a millennium has passed. You emerge into a civilization that has had 10 centuries to evolve, to change, to forget. The language you speak could be as ancient to them as Old English is to us. The very concept of a nation-state, of money, of the family unit might be unrecognizable relics. You would be the ultimate outsider, a living fossil washed up on the shores of a world that has long since moved on. Your knowledge, your skills, everything that defined you would be obsolete. How would you find purpose or even basic companionship in a society so advanced you cannot even comprehend its foundations? The psychological weight of that permanent dislocation is almost too heavy to contemplate. But what if the future is not one of glorious advancement, but of quiet decline? Your one-way ticket could just as easily deliver you to a silent, post-apocalyptic Earth. The star you traveled to might host a dead world, scoured by radiation or stripped of resources. There would be no rescue mission, no way to signal for help, and certainly no path back. You would be alone, the last visitor to a museum of a dead civilization, with all of eternity to ponder your choice. This is the fundamental gamble of the Krasnikov Tube. It demands that you bet your entire existence on the trajectory of a universe you cannot control. Do you trust humanity or life itself to persevere and flourish over cosmic timescales? Or do you accept that your journey might end in absolute final solitude? Stepping into the tube is the ultimate act of faith, a commitment to a future you can only hope is waiting for you. This permanent farewell is exactly why storytellers find the Krasnikov Tube so magnetic. Its one-way nature provides a powerful engine for narratives of sacrifice, exile, and the ultimate unknown. While the tube itself has not yet stepped into the Hollywood spotlight, its conceptual siblings have driven some of science fiction's most haunting plots. Consider the Generation ship, a vessel where inhabitants live and die during a centuries-long journey. This is a one-way trip in time, a slow version of the tube's promise, where those who arrive can never return to the world that launched them. A more direct parallel can be found in the stargates of popular fiction, those shimmering portals to other worlds. but imagine if one of those gates, once stepped through, ear-eyes shut and vanished forever. That is the narrative power of the Krasnikov Tube. It forces a character's hand, creating an absolute point of no return. A story could begin with a team of scientists voluntarily entering the tube to save a dying Earth, carrying human knowledge to a new world they know they will never see. They are not explorers, they are seeds cast into the cosmic wind, and the drama comes from their struggle to build a new society with the full weight of their old one vanished behind them. Alternatively, the tube could be a setting for profound exile. A criminal might be offered a choice: life imprisonment or permanent ejection through the tube to an uncharted destination. This is not just a physical punishment, but a temporal one, a sentence served in a future where even the memory of their crime has been erased. The tube becomes the ultimate justice, a punishment that is also a terrifyingly blank slate. For audiences, these stories tap into a deep-seated fear and fascination with finality. What would you be willing to give up forever? What would you risk for a single, unrepeatable chance? The Krasnikov Tube, in the hands of a storyteller, is not just a tunnel through space, but a crucible for the human spirit, testing what we value when every bridge is burned. A functional Krasnikov Tube would be far more than a cosmic curiosity. Its true value lies in applications that demand a permanent solution, where the finality of the journey is not a flaw but the entire point. The most immediate use would be for interstellar probes. We could dispatch robotic scouts to thousands of star systems, each one carrying a one-way data stream back to Earth. These machines would be our eyes and ears, reporting on alien worlds and cosmic phenomena for centuries, even millennia after their launch. The profound benefit is that we would not need to solve the problem of bringing them home. We invest in a single, permanent launch and gain a window to the galaxy for all of future humanity. Of course, the con is the agonizing delay. A probe sent 1,000 light-years away would take 1,000 years for its first signals to even reach us. We would be planting trees whose shade we would never enjoy, a gift to descendants so far removed we cannot picture their world. A far more urgent application would be planetary evacuation. If our world faced an unavoidable and extinction-level threat, a dying sun or an unstoppable asteroid, the Krasnikov Tube could serve as the ultimate lifeboat. It would be a mass exodus, a desperate one-way trip for a chosen few to carry the embers of human civilization to a new world. The pro is simple: it offers a chance for survival when every other door has closed. It turns certain extinction into a precarious chance at continuity. But the cons are ethically staggering. Who gets to go? How do you choose which people, which cultures, which genetic lines are saved and which are left behind to perish? The tube becomes a symbol of the most brutal triage imaginable, a permanent severance not just from a planet but from the vast majority of the human family. This leads directly to the concept of one-way colonization. Unlike a probe or an emergency exit, this would be a deliberate, planned migration. The advantage is the establishment of a truly independent branch of humanity. Freed from the possibility of return, the colonists would be forced to adapt completely to their new world. There would be no safety net, no option to turn back when things get difficult. This could forge a resilient and fiercely independent society, one that evolves on its own unique path. The downside is the psychological toll of that very permanence. The colonists would live with the knowledge that everyone they knew on Earth is not just far away but centuries dead. They would be living in the future, disconnected from their own past, a form of cultural and historical orphanhood. Every story, every song, every memory from the old world would become a ghost haunting their new one. The Krasnikov Tube, in this light, is not just a transportation device. It is a machine for creating irrevocable choices, forcing us to weigh the survival of the species against the soul of the individual. This cosmic river demands a fuel that defies reality itself. To carve a permanent scar in spacetime, the energy required is not just immense, it is categorically impossible by our current standards. We are talking about energies that rival the total output of a star, concentrated and manipulated with a precision we cannot even conceive. But the true showstopper is not just the quantity of energy, it is the quality. The mathematics of general relativity points to a need for something far stranger, a theoretical substance known as exotic matter. This is not merely a new element on the periodic table, it is a form of matter that turns the known laws of physics inside out. Normal matter, everything you can see and touch, possesses positive energy density. It creates gravity, it pulls space-time inward, it attracts. Exotic matter would do the exact opposite. It would have negative energy density and negative pressure. Think of it as a kind of cosmic repulsion glue. If you tried to build the Krasnikov Tube with normal matter, the immense gravity would instantly crush the tunnel into a singularity, a black hole from which nothing could escape. To prop the tunnel open, to keep the walls of this cosmic passage from collapsing, you need this exotic matter to line the tube, pushing space-time outward with a force that counteracts its own natural tendency to implode. It is the only thing that could keep the door from slamming shut the moment you try to open it. The problem is, we have no proof that such a substance can exist in a stable, useful form. In the quantum realm, fleeting glimpses of negative energy appear as virtual particles blink in and out of existence, but these are microscopic fluctuations that vanish in an instant. Harnessing this effect, amplifying it to a macroscopic scale large enough to build a tunnel through the stars, is a challenge that may be fundamentally insurmountable. It is like trying to build a dam using only the brief splashes from individual raindrops. Without a revolutionary discovery that unlocks the secrets of exotic matter, the Krasnikov Tube remains a ghost in the machine of theoretical physics, a blueprint for a bridge we have no material to build. The engine behind this cosmic one-way street is a specific set of numbers, a mathematical recipe that tells spacetime exactly how to bend. Sergei Krasnikov did not invent his tube out of thin air. He discovered it as a valid solution to Einstein's field equations, the very rules that govern how matter and energy shape the cosmos. To grasp this, you need to understand the concept of a metric tensor. Do not let the technical name intimidate you. Think of the metric as the universe's master blueprint, a set of instructions that defines the geometry of reality at every single point. In our everyday flat space, this blueprint is simple. It tells us that the shortest distance between 2 points is a straight line, a rule we learn in grade school. But near a massive object like a star, that blueprint changes. The numbers in the metric tensors shift, and now the shortest path is a curve, which we experience as the force of gravity. Krasnikov's genius was in writing down a very specific, very strange set of numbers for this metric. His mathematical recipe does not describe a gentle curve. Instead, it defines a region where space is compressed directly in front of a traveler's path and expanded behind it, all while locking this distortion into a permanent, stable configuration. The specific values he assigned create a geometry where the path forward is a downhill slope, a slide through the cosmos, while the path backward is an insurmountable cliff. This is not a matter of engineering or willpower, it is a fundamental property written into the fabric of that region of space by the metric itself. The numbers themselves forbid a return journey, creating a one-way tube not by force, but by the intrinsic, unchangeable curvature of the reality it defines. For all its mathematical elegance, the Krasnikov Tube faces a wall of profound skepticism from the very community that gave it birth. Theoretical physics is a playground of the mind, but its ideas must eventually face the harsh judge of physical reality. A common refrain from critics is that a solution being mathematically valid does not mean the universe will permit it to exist. The equations might allow for a one-way street through space-time, but the construction materials are pure fantasy. The foremost objection is, of course, the exotic matter requirement. Nobel laureate Kip Thorne, whose own work on traversable wormholes paved the way for such ideas, has been openly doubtful about the physical plausibility of these structures. He points out that while negative energy densities can appear in specific quantum contexts, the idea of gathering and stabilizing this exotic substance in the vast quantities needed to prop open a cosmic tunnel is almost certainly impossible. It is like a recipe that calls for unicorn horn shavings. The instructions are clear, but the key ingredient does not exist in our world. Even if we could somehow produce it, many physicists believe this exotic matter would be inherently unstable. The moment you tried to assemble enough of it to build your tube, it would likely decay into a burst of ordinary particles or trigger a catastrophic collapse, instantly undoing your work. The tube is not just a construction project, it is a constant battle against the universe's own tendency to smooth itself out, to erase such violent wrinkles in its fabric. This leads to the criticism of quantum instability. The vacuum of space is not truly empty, it is a seething foam of virtual particles popping in and out of existence. Theorists like Stephen Hawking suggested that this quantum frenzy would inevitably destroy any such structure. The moment you create a shortcut through space-time, these quantum fluctuations would be amplified to devastating levels, flooding the tube with unimaginable radiation or causing it to pinch off into a singularity before anyone could ever use it. The Krasnikov Tube, for all its conceptual brilliance, might be like a sandcastle built at low tide, mathematically perfect in design, but doomed to be erased by the next wave of quantum reality. This quantum world offers a glimmer of hope, a potential loophole in the universe's strict no-construction policy. To find it, we must shrink our perspective from the cosmic scale down to the subatomic realm, where the rules of reality become fuzzy and strange. This is the domain of quantum mechanics, and it might just hold the key to the exotic matter we so desperately need. The most tantalizing clue comes from a laboratory phenomenon known as the Casimir effect. Imagine two perfectly smooth, uncharged metal plates placed incredibly close together in a vacuum. According to classical physics, nothing should happen. But in the quantum world, that vacuum is not empty. It is a bubbling sea of virtual particles constantly flickering into and out of existence. These plates are so close that they limit the kinds of quantum fluctuations that can appear between them. The result is that more virtual particles push on the outside of the plates than on the inside. This creates a tiny but measurable force that pushes the plates together. Crucially, the energy density between those plates is effectively negative. For that tiny sliver of space, we have created a region with less than zero energy, a microscopic sample of the exotic matter the Krasnikov Tube requires. It is real, it is measurable, and it proves that negative energy densities are not entirely forbidden by the laws of physics. The problem, of course, is one of monumental scale. The Casimir effect produces a whisper of negative energy, while building a Krasnikov tube would require a continuous, roaring hurricane of it, sustained across light years of space. Bridging that gap is perhaps the greatest engineering challenge imaginable. Could we somehow weave together countless trillions of these microscopic Casimir cavities to line our cosmic tunnel? Or does quantum mechanics offer another path entirely through the nascent theory of quantum gravity? This is the holy grail of modern physics, a sought-after set of equations that would finally unite Einstein's general relativity with the quantum world. Some theories, like string theory or loop quantum gravity, suggest that on the tiniest possible scale, the fabric of spacetime is not smooth but granular, made of discrete, vibrating units. This fundamental graininess could, in theory, prevent the infinite tidal forces and destructive energies that classical physics predicts would rip a Krasnikov tube apart. The violent quantum fluctuations that Hawking warned of might be naturally smoothed out by this underlying structure. In this view, the tube might not be a sandcastle facing the tide, but a structure built from the very sand itself, inherently stable within a grainy universe. Yet this remains a beautiful speculation. We do not yet have a complete theory of quantum gravity, and without it, we cannot know if it would be a friend or foe to the cosmic architect. The promise is there, a faint signal from the quantum noise suggesting that the universe's building blocks might allow for these strange shortcuts after all. But until we can decode the full blueprint of reality, the Krasnikov Tube remains suspended between two worlds, a child of relativity that is waiting for its quantum parent to give it life. The Krasnikov Tube is not alone in its cosmic ambition. Other theoretical structures whisper of similar shortcuts, each with its own strange rules and tantalizing possibilities. Take the idea of a Krasnikov superluminal highway, for instance. This is not a single tube, but an entire network of them, a sprawling interstellar freeway system laid down by a civilization with godlike control over space-time. Imagine a future where humanity, or something else, has paved permanent routes to the stars. You could travel from Earth to a colony in the Andromeda galaxy, then take a different one-way on-ramp to a world in a completely different galactic cluster. The journey through each tube is still a permanent one-way relocation, but the network itself offers a kind of nomadic existence, a life spent forever moving forward through the cosmos with no home port to return to. It is a vision of a universe stitched together by one-way streets, where every destination is a new beginning and every arrival is a final farewell to your last stop. This highway system shares the same fundamental constraint as the single tube. Its architecture is a permanent firewall against paradox, but it scales the implications up to a truly galactic civilization. Then there are cosmic strings, hypothetical defects in the fabric of the universe left over from the Big Bang. Think of them as infinitely long, incredibly thin cracks in reality, filaments thinner than an atom but with the mass of an entire galaxy. The spacetime around a cosmic string is so severely warped that if you were to fly a spaceship around one, you could, in theory, arrive back at your starting point before you even left. This creates a natural time machine, a closed time-like curve that seems to violate causality in the most direct way possible. This is where the Krasnikov Tube stands apart. While a cosmic string offers a potential round trip through time, inviting all the paradoxes that come with it, the Krasnikov Tube is meticulously designed to avoid that exact scenario. Its one-way geometry is not a flaw of the model, it is its core safety feature, a deliberate choice to keep the universe logically consistent. Other wormhole solutions face the same instability. The classic traversable wormhole proposed by physicists like Kip Thorne and Morris allows for two-way travel, but it requires immense amounts of exotic matter just to stay open for a single journey. More than that, many theorists believe that the moment you try to use such a wormhole for time travel, the quantum feedback would become infinite, vaporizing the tunnel in an instant. The universe seems to have a zero-tolerance policy for paradox, and it will destroy any bridge that threatens to create one. The Krasnikov Tube, by contrast, is a structure the universe might actually tolerate. It trades the dream of a round trip for the stability of a permanent exit. It does not try to fight the universe's rules on causality. It finds a clever, almost respectful way to work within them. It is the difference between trying to build a bridge that can carry traffic in both directions over a bottomless chasm and simply deciding to build a one-way chute to the other side, accepting that you can never go back. In the theoretical landscape of cosmic shortcuts, the Krasnikov Tube is not the most glamorous option, but it might just be the most pragmatic, a solemn acknowledgement that some doors, once opened, are meant to be closed behind us forever. This one-way journey forces us to confront a moral chasm as vast as the cosmic distances it spans. The fundamental ethical question is stark: is it ever right to send a conscious being on a voyage of no return? For a volunteer explorer, the choice might be clear: a sacrifice for knowledge or the survival of the species. But the line blurs quickly. Would we send teams of scientists knowing they are accepting a life of permanent exile? Their consent would need to be absolute, informed by the crushing weight of their finality. This is not a long-term mission with retirement plans. It is a deliberate severing from all of human history and everyone in it. The ethical burden on those who remain, the mission controllers who press the button and then watch the tunnel seal shut, would be immense. They are not just launching colleagues, they are effectively presiding over a living funeral. And what if the volunteers are not fully aware of the psychological toll? Can anyone truly comprehend the depth of isolation they will face until they are living it, alone in a future they can never leave? The moral responsibility extends beyond the travelers to the society that builds the tube. Creating such a technology is an act of profound power, and with that power comes the terrifying potential for misuse. Imagine a government declaring the tube the ultimate penal colony. Instead of life imprisonment, the most dangerous criminals are offered a choice: execution or permanent exile to a future era. On the surface, it might seem merciful, a chance at life, but in reality, it is a punishment of unimaginable cruelty. You are not just sent away, you are erased from your own time, cast adrift in an era where you have no context, no connections, and no hope of ever understanding your new world. It is a fate arguably worse than death, a sentence of perpetual alienation. This opens a door to a new form of despotism, where dissidents and political enemies are not just silenced but surgically removed from the timeline itself. The very existence of the tube creates a tool for absolute and irreversible oppression. The ethical dilemmas become even more tangled when we consider sending only information. Is it moral to dispatch a capsule containing all of human knowledge, our art, our history, our science, to a future we can never visit? We will be placing a tremendous burden on the recipients, forcing them to curate and interpret a civilization that is, to them, ancient history. We would become ghosts haunting their culture, our values and mistakes preserved in digital amber, potentially influencing their development in ways we cannot predict. The act of sending is an act of interference, even with the best intentions. The philosophical depth of this is staggering. The Krasnikov Tube forces us to define the very limits of human agency and consent. It asks who has the right to make a decision that can never be undone, and what we owe to those who pass through a door that locks behind them forever. This cosmic silence might hold the answer to one of our greatest questions. We gaze at a universe that should be teeming with life, yet we hear nothing but an eternal quiet. This is the Fermi paradox, the haunting contradiction between the high probability of alien civilizations and our complete lack of evidence for them. We have asked for decades, where is everybody? The Krasnikov Tube offers a chillingly simple and profoundly final possibility. What if they are not out there because they have all moved on? Imagine an advanced civilization reaching the technological pinnacle where building these one-way tunnels becomes possible. After exploring their local star systems, they face the same limitations we do, the agonizing slowness of light and the crushing finality of time. So they make a choice. They commit to a permanent migration, firing off colony ships through Krasnikov tubes to the far future of distant galaxies. They are not hiding from us. They have simply left our present moment behind, traveling to a time so far ahead that our entire civilization, from its birth to its extinction, is just a blink in their rearview mirror. They cannot come back to visit us, not because they do not want to, but because the very physics of their transportation forbids it. The tube is a door that only swings outward, and they have stepped through, leaving our epoch forever. We are not alone in the universe. We are just tragically early, or they are impossibly late for a conversation that can never happen. Our sky is empty not because life is rare, but because the ultimate end goal of intelligence is to graduate from its home time, becoming a species of permanent pilgrims forever journeying into tomorrow. This transforms the great filter, the hypothetical barrier to widespread galactic life. Perhaps the filter is not a cosmic catastrophe that destroys civilizations, but a technological destiny that removes them from the observable universe. The most advanced beings may not die out, they simply depart, leaving behind silent, empty worlds as monuments to their passage. We look for radio signals and Dyson spheres, but the real evidence of a great civilization might be the absence it leaves behind, a star system with no one home because everyone has taken the ultimate one-way trip. The greatest challenge in sharing this idea is that it exists only as a set of equations on a page. How do you paint a picture of a tunnel made not of matter, but of geometry itself? The answer lies in the collaboration between science and art, forging visual metaphors that can bridge the gap between abstract theory and human understanding. Imagine a vast, dark sheet stretched taut, representing the flat fabric of space-time. This is our canvas. Now, a force begins to warp this sheet, pushing down on one point and pulling up on another far away until the 2 points draw near, connected by a shimmering, tubular passage. This is the Krasnikov Tube, visualized not as a physical structure, but as a permanent crease in reality. Computer-generated animations are our most powerful tool for this, allowing us to show a spacecraft approaching this distortion. The ship does not fire thrusters to enter. Instead, it is caught by the cosmic current, sliding smoothly and silently down the one-way slope. The moment it passes the midpoint, the entrance behind it seems to dim and stretch away, becoming unreachable, while the exit ahead brightens, pulling it forward. This visual makes the tube's irreversible nature viscerally clear. The artists who create these animations work hand in hand with physicists, translating dense mathematical symbols into flowing, intuitive imagery. They are not just illustrators, they are translators of the cosmos. Their visual metaphors, like the rubber sheet for space-time, are not literal truths but essential gateways. They take a concept that bends the mind and give it a form our eyes can follow, making the profound strangeness of a one-way cosmic street something we can all, for a moment, almost see. Yet for all its mathematical elegance, the Krasnikov Tube remains a ghost in the machine of physics, entirely untested by any experiment. There is not a single piece of observational evidence that such a structure exists in our universe. These cosmic one-way streets are purely theoretical solutions to Einstein's equations, beautiful patterns woven from the fabric of mathematics itself, but patterns we have never seen painted across the actual sky. So how could we ever hope to find one? The search would be a hunt for the most subtle of cosmic footprints. One potential signature would be a bizarre form of gravitational lensing. We are familiar with how the gravity of a massive object like a galaxy bends light from stars behind it, creating duplicate images or Einstein rings. A Krasnikov tube, a permanent warp in space, would create a lensing effect unlike any natural object. Instead of a symmetrical distortion, it might produce a strange, one-sided smear of light, a telltale sign that space itself is bent into a one-way slope in that particular region. An even more definitive clue would be the detection of exotic matter. If we could somehow scan a region of space and find a persistent, macroscopic volume of matter with negative energy density, it would be the smoking gun, proof that the universe allows for the fundamental building block of these tunnels. But the challenges here are astronomical. The exotic matter signature would be incredibly faint, and the tube itself would be a thread finer than a human hair, lost in the unimaginable vastness between stars. Our current telescopes are not designed to look for such specific, subtle anomalies. We would need a new generation of observatories, instruments capable of mapping the detailed geometry of spacetime itself across light years, searching for the faintest wrinkles that betray a permanent scar. For now, the Krasnikov Tube is a reminder of the vast gulf between what our mathematics says is possible and what our instruments can confirm. It is a map to a destination we have not yet found, a set of coordinates for a door we cannot prove is even there. The equations that describe this one-way tunnel are not collecting dust on a shelf. A small but dedicated group of theoretical physicists continue to probe the edges of this idea, not because they expect to build one next year, but because the tube serves as a perfect testing ground for the laws of physics themselves. The central puzzle they are trying to solve is whether the universe's rulebook, when read in its entirety, actually permits such a structure to exist. This is where the quest for a theory of quantum gravity becomes paramount. Our two most powerful descriptions of reality, general relativity and quantum mechanics, are currently at odds. General relativity paints the beautiful, large-scale picture of warped spacetime and cosmic rivers. Quantum mechanics describes the frantic, probabilistic dance of the subatomic world. They are both brilliantly successful in their own domains, but they violently disagree on what happens in the extreme conditions a Krasnikov tube would create, like at the boundaries of the tunnel itself. Uniting these two theories into a single framework of quantum gravity is perhaps the greatest unsolved problem in all of physics. Promising candidates like string theory and loop quantum gravity are the front runners in this cosmic unification effort. String theory proposes that the fundamental constituents of reality are not point particles, but unimaginably tiny, vibrating strings. The different vibrations of these strings give rise to all the particles and forces we see. In this framework, spacetime itself might be an emergent property from a deeper, more fundamental layer of strings. This could completely change our understanding of whether a Krasnikov tube is stable. The violent quantum fluctuations that classical physics predicts would destroy the tube might be naturally smoothed out or redefined by this underlying stringy nature of reality. It could be that the tube is not a classical structure at all, but a quantum one held together by the intricate interplay of these cosmic strings. Loop quantum gravity takes a different but equally mind-bending approach. It suggests that space itself is not smooth and continuous, but is woven from a fabric of tiny, discrete loops, a kind of atomic structure of spacetime itself. This pixelation of reality at the smallest possible scale, the Planck length, could provide a natural cutoff that prevents the infinite forces and energies that would otherwise rip a Krasnikov tube apart. In a grainy universe, you cannot have an infinitely sharp curvature, which means the tidal forces inside the tube might be severe, but not instantly catastrophic. The tube's geometry could be fundamentally compatible with this granular spacetime, a permanent feature woven into the very fabric of the cosmic quilt. Researchers are actively using the mathematical tools of these theories to stress-test the Krasnikov model, asking if its one-way geometry can survive the transition from a classical to a quantum universe. The answers are not yet in, but the very act of asking pushes our understanding of causality, geometry, and the fundamental architecture of existence. This is not engineering, it is the most profound kind of exploration, a journey into the logic of reality itself, using the Krasnikov tube as our guide. The journey of the Krasnikov tube from a dense physics paper to a popular science staple is a story in itself. It began in the academic journals of the late 1990s, a technical solution buried in complex tensor calculus, read by only a handful of specialists. Its path into the public consciousness was paved by science communicators who recognized its profound narrative power. Documentaries exploring the edges of physics gave it a visual form, using computer animations to transform abstract mathematics into a shimmering, one-way tunnel through the stars. Online forums and communities dedicated to futurism and theoretical physics lit up with discussions. Enthusiasts debated its implications not as physicists but as storytellers and philosophers, asking what they would pack for a journey from which they could never return. Science channels on video platforms dissected its mechanics with clear, engaging graphics, making the impossible seem almost tangible. So why did this idea, among so many other wild theories, find such fertile ground in our collective imagination? The answer lies in its stark finality. The Krasnikov tube is not just a faster-than-light drive, it is a metaphor for the ultimate choice. It taps into a deep, almost primal fascination with points of no return. We encounter them in our own lives, the decision to leave a hometown, to end a relationship, to commit to a path that changes everything. The tube magnifies this human experience to a cosmic scale. It embodies the terrifying and thrilling prospect of burning all your bridges, of committing to a future so completely that the past becomes a locked room you can never enter again. This resonates more deeply than the technical wonder of a warp drive. It is a concept that forces introspection. It asks us what we would be willing to leave behind forever for a single, unrepeatable chance at a new beginning. That is a question that transcends physics, connecting directly to the very core of the human story. These cosmic one-way streets are often misunderstood, twisted into something far simpler than their reality. It is vital to clear the air of science fiction fantasies and grasp what a Krasnikov tube truly is not. First and most importantly, this is not a time machine in the classic sense. You cannot use it to travel back to the year 1920 to witness a historic event or to alter the course of your own personal history. The tube's architecture slams the door shut on any journey to the past. Its entire design is a safeguard against the very paradoxes that make time travel so problematic. You are not stepping into a machine that lets you hop between centuries like stations on a subway line. You are stepping onto a moving walkway that only goes forward, carrying you relentlessly toward the future. This leads to the second great misconception, the idea that this is a proven or observed phenomenon. We have never found one. There is no cosmic signpost pointing toward a Krasnikov tube in a nearby nebula. It is a fascinating what-if scenario, a ghost that lives entirely within the elegant mathematics of general relativity. The equations suggest that if you could manipulate space-time in this very specific way, this is what you would get. But the universe is under no obligation to make that possibility a reality. It remains a thought experiment, a powerful tool for probing the edges of our physical laws, not a description of an existing piece of cosmic engineering. It shows us a door that might be possible to build without confirming that the door is actually there. The Krasnikov tube stands as a haunting monument to human curiosity, a one-way tunnel through reality that promises the stars at the cost of everything you have ever known. Our journey through its concept reveals a structure built not from steel, but from the raw geometry of space-time, a permanent exit door carved by energies beyond our grasp and materials that may not exist. It is a theoretical marvel that simultaneously illuminates and humbles, showing us just how far the mathematics of relativity can stretch, while highlighting the monumental, perhaps insurmountable, practical walls that stand between a brilliant equation and a functioning machine. This one-way street forces us to confront staggering questions about our place in the cosmos. Would we use such a technology for salvation, casting the seeds of humanity into the void to escape a dying Earth? Or would it become the ultimate instrument of exile, a silent, irreversible punishment? The tube challenges our very understanding of choice and consequence, of what it means to make a decision that can never, ever be undone. It touches on the profound silence of the Fermi paradox, suggesting that advanced civilizations may not be missing, but simply gone, having departed our present moment for futures we cannot follow. Ultimately, the Krasnikov tube is more than a physics puzzle. It is a mirror reflecting our deepest desires and fears. It speaks to that timeless human yearning to conquer the vast distances between stars and to reach beyond the limits of our own mortality. Yet it also reminds us that some doors, once opened, change not just where we are, but who we are, locking the past away forever. So we are left to wonder, if you were faced with that ultimate one-way journey, what would you be willing to leave behind, and what would you hope to find waiting in the light at the end of that tunnel? Share your own thoughts on this incredible idea in the comments below.